Well, welcome everybody. I'd like to welcome our speaker, Urmila Diwekar, who's joining us to talk about an efficient optimization under uncertainty framework for static and dynamic sensor placement. And she has some real-world applications to power systems, water distribution networks, and air pollution monitoring. I'd like to just read a brief bio abstract. She is the winner of our 2022 CAS division for AICHE Computing Practice Award, which was one of the most prestigious awards from this CAS division. And as part of this, we invite the award winners to give a presentation on their work and some of their perspective. She is currently the president of a nonprofit research organization, Stochastic Research Technologies, and VRI. She founded in 2004 to pursue multidisciplinary research. And from 1991 to 2002, she was on the faculty at Carnegie Mellon University. From 2002 to 2004, she was a professor in the Department of Chemical Engineering, Bioengineering, and Industrial Engineering at the University of Illinois at Chicago. And in chemical engineering, she's worked and is well known in the areas of simulation design, optimization, control, stochastic modeling, and synthesis of chemical processes, especially batch processes. She's the author of more than 200 research papers, 7 books, 15 book chapters, and has given over 400 presentations and seminars, many of these invited presentations. Her work has been cited 6,700 times, and she has an H-index of 44. She's advised 46 graduate students and 15 postdocs. Her list of awards is impressive as well. She, in 2009, received the Clarence Gerhold Award. 2011, she received the Cecil Award for Environmental Chemical Engineering. In 2015, she received the Energy and Sustainability Award. 2011, the Teeley Award for contributions to chemical engineering, and now with this award in 2022 for the CAS Division Computing Practice Award. She's a fellow of AIMBE and also a fellow of AICHE. So let's welcome Urmila today for this talk, and go ahead and start sharing. Thank you, Urmila. Welcome.
Thanks, John. Thank you for the kind introduction. If you cannot hear me or have any problems, just send a chat so that John can inform me. Can you, I think, can you see
we
my
can
screen?
see it.
I know the title is long. Wanted to put more in terms of applications. So I won't get into the details of the algorithmic part, but if you need more information, send me email. I can send you papers and I can refer you to the books. So my email is given here, urmila@vri-custom.org. So you can contact me at any time. So my topic today, I'm going to talk about both static and dynamic sensor placement in various applications like power plants, which is like a chemical process plant, water distribution networks, and air pollution monitoring. So this is a work funded by different agencies. And I'm sorry, I forgot to put the thing, National Science Foundation, DOE, as well as EPRI, Electric Power Research Institute, at various points. And many people contributed to this. Some of my students and postdocs, and their names will come later. Sensors, what do? In power systems and chemical plants? Actually, they help us to estimate values of parameters for plant operation, control, and monitoring. Okay, so it's very important because if your measurement is not right, your control and other things will not work, and that's why sensors are necessary. In drinking water and distribution network, one of the things is that you have been connected to different population centers, and essentially what is this impact of if some contaminants get into water on different populations, and whether we can stop that flow where the contaminant concentrations are high. In air pollution monitoring, to monitor pollution at various locations in the city or in the atmosphere. So you have different kinds of things. Now, one of the things is that why sensor placement is important is because you need multiple sensors actually to monitor a network, but you cannot put large number of sensors because it can become expensive and it can be prohibitive. So you want to place sensors in an optimal way so that you can maximize the information. Okay, so you want to find how many sensors are needed, minimum sensors are needed, what type, and where the location of sensor should be. So that's why sensor location problem, sensor placement problem is important. And most of the sensor placement problem actually maximize information. We in my group use Fisher information as an objective to be maximized. You will see this equation, it's a probabilistic term. Fisher information actually is a measure of observability. So observability between measured variable X and actually estimated parameter pollutant theta, and it is given by this this equation, integral equation. Okay, so Fisher information can be obtained for stationary as well as dynamic sensing. Now, what is this static and dynamic sensing? We are aware of in the power plant, actually, we have sensors placed at different points. There are gas sensors, there are pollution sensors, temperature sensors, pressure sensors, and things like that. And they are placed permanently at that point. So that in air pollution monitoring stations, the stations are fixed at certain places. Similarly, in water distribution networks, the sensors can be placed and fixed. But what happens with this case of static sensing is that you will not get the idea of spatiotemporal changes. So that becomes a factor, and these in recent places, in fact, I started working about in dynamic sensing because I read an article that this was some few years back. In China, the pollution was so high that people were putting sensors on kite and sending kites in the atmosphere to measure the pollution. So that kind of dynamic system in a sensing where the sensor the positions can change dynamically becomes important to actually monitor this thing. And now even in water and in case of air pollution, you can have portable sensors. Okay, if you have portable sensors, or for example, air pollution monitoring, you could have drones, sensors on the drones to monitor air pollution. Then becomes a problem of dynamic sensing. How do you spatio-temporally place these sensors? How do you change the positions as the dynamic changes? And that is dynamic sensing problem. It's important because situations can change dynamically, as well as because of uncertainties and things can change also. So you need to have dynamic sensing problem. Now, one of the things is that what I'm going to use an efficient framework for static and dynamic sensor placement. It is, as I said, Fisher information, if you look at it, it's a probabilistic information. So it's a probabilistic objective function, as well as what happens is that we consider sensor error measurements can be probabilistic too, and that becomes an optimization and uncertainty problem. It's a mixed integer, nonlinear programming problem. So this kind of problem, is difficult because depending on how big the problem becomes. Now, in case of power plants or chemical plants, I'll show you a case study of a static sensor placement. But what happens if you have wireless sensors where you can shut off and shut on certain number of sensors? That becomes dynamic sensing. And in that case, you need to have an algorithm which is real-time algorithm which can optimize these sensors. So mixed integer nonlinear programming problem becomes difficult. So what we do in our group is we actually use the sensor measurement characteristics. If you don't have any sensors, your error in calculation of that variable is higher. Okay, if you have sensors, depending on the cost of sensor, your error characteristic can change. Using this information, we can convert the problem of mixed integer nonlinear programming into stochastic mixed integer nonlinear programming into stochastic nonlinear programming problem. And once it is stochastic nonlinear programming problem, we use an algorithm called bonus, better optimization of nonlinear uncertainties. How this is different than most of the stochastic nonlinear programming approaches, if you look at stochastic programming literature, you will see that to solve optimization under uncertainty problem, people assume that uncertainty information is known in a particular form, and you can actually maybe transform it into chance constraint method, okay? Something where you can transform it into a deterministic optimization problem. But chance constraint has limitation because it assumes stable distributions, and uncertain variable has to be included in a linear function. And it divides the problem into stages. This cannot be applicable to large scale problem, the one which I'm going to talk about. First thing is that there is no linear function, and the distributions of uncertainty may not be stable. The other thing which people apply is decomposition techniques, which they generate bounds by solving subproblems. That requires some convexity conditions and as well as open equation thing, and cannot be used. So what we have is we actually use algorithm, as I called, is better optimization of nonlinear uncertain systems. If you look at optimization under uncertainty problem, you have optimization and you have uncertainty. Uncertainty many times is assumed as scenarios, but in this case, for a large scale problem, they are samples. And essentially what happens is that these two loops interact with each other to give you solution. And one of the things, advantage of better bonus algorithm is that it can be applicable to black box models like Aspen, EPNet, which I'm going to talk about, all these big simulators, as well as AirMod, which is an air pollution monitoring simulator. So that's why we use this. How bonus is different. This is a general approach to stochastic optimization problem. You have optimization problem on the top of scenario generation or sampling generation, okay, which gives the probabilistic information to the optimizer. These are two different loops, but the loop which is very expensive in general in any stochastic programming problem is the inner red loop, because you need to, if you have something like 2 to 3 uncertain variables, you should at least have 100 samples, while optimization may take something like 5 to 10 iterations. So this is very expensive. So what bonus does is actually uses efficient sampling techniques. We have in my group, we develop a lot of sampling techniques. So Monte Carlo, Latin hypercube, Hammersley, LHS, HSS, Sobol, and LHS Sobol. And depending on how many uncertain variables you have, you can choose the sampling technique. And this sampling technique is order of magnitude faster than any Monte Carlo or Latin hypercube sampling technique. So we use that. The other thing we do is actually only in one first iteration, we use sampling, and the whole loop of modeling and sampling is eliminated in the successive iterations. So it becomes very fast. How we do that? In general optimization, what we have is decision variable is a single value between upper bound and lower bound. And uncertain variable has some uncertainty. In our problem, what we say is that even the single value is a single distribution, which is a very narrow normal distribution around that value. Why we do it? Then we can use the sampling actually to use something similar to Bayes update, but Bayesian update formula. So in first iteration, we say everything in decision variable is between uniform distribution, when certain variables will keep their distribution. And as the iteration progresses, the value of the decision variable change, where we have a small, narrow normal distribution. What we use is a theory from statistics. what theory says is that if you know input probability, and if you propagate the sampling and get output probability for that distribution, if you change the distribution of the input, you may not have to go through the sampling again. You can use the probability estimation, probability distribution of the base case, probability function of the change distribution, and the probability function of the output distribution, base case output, to get the probability distribution of the new distribution, output distribution. So you don't have to worry about, if you know this formula, you don't have to go through the model sampling loop again. So we use it. I'm not getting into the formula, but essentially what it means is that instead of having this thing, you only have reweighting scheme, which becomes also important because the stochastic nonlinear programming problem is almost changed into most of the linear form. Okay, but we use nonlinear programming algorithm. So this is the general approach, and essentially it's very fast so that you can solve real world problems. One of the things we are going to do is now go to the applications in the sensor placement. And sensor placement application, the first application I'm going to talk to you about sensor placement in a power plant. As chemical engineers, we recognize a power plant as a chemical process. And most of you have used some simulators like Aspen or Pro2 or other ChemCAD simulator to simulate a chemical process. We use Aspen to simulate this. Now, one of the things is that this was given to us by DOE, and the problem was we want to not only place sensors such that it improves observability of the plant, but as well as efficiency of the plant. Okay, so we had multiple objectives, and actually we implemented bonus in Aspen. Okay, and we could carry out bonus plus sampling, and we could carry out the optimization. And what we did is the same thing. We assume that different nodes have different sensors, and if at that point sensor is placed, depending on the cost of the sensor, the error characteristic change. If there is no sensor, there is a 20% uncertainty. If it is low cost sensor, 5%. If it is medium cost, low cost is 5%. Medium cost is maybe this thing. Okay, high cost sensors have 1%, medium cost sensors have 2.5%, and low cost sensors are 5% error. And if you don't have a sensor, you are actually going to get larger error, that is 20%. By doing that, we eliminated the sensor, the mixed integer part of it, because we have distributions for each cases. And that helps also in the stochastic programming problem. We got the solution. Here is 3 objectives. We wanted to maximize efficiency, which is on x-axis. X and y-axis is efficiency and Fisher information, and z-axis is the cost. And essentially, we got multiple solutions. Now, this is, if you look at the blue ones, we consider low cost, medium cost, and high cost sensors. And if you can, blue lines is just high cost sensors, and red dots are combinations of low, medium, and high cost sensors. And you will see that we found some of the best solutions are given here. So if you take Fi as an objective function for maximizing Fisher information, you essentially got these 2 solutions. One is if I consider combination of low cost, medium cost, and high cost sensors, I will actually have cost is given in terms of, I think, if I am right, it is 5.275 million. And essentially efficiency was 43%, which is high efficiency. And we have sensors given here where it should be H is high cost, medium is M, and L is this thing. If you only consider high cost sensor, you can have the same cost, but the Fisher information is lower, but efficiency is higher, and you will see this cost. Okay, so you can have different sensor combinations if you want, if you consider low cost or high cost sensors. Okay, so this is what happens about power plant. As I said, this is the static sensor network where we are actually fixing the sensors for that plant. But if you want to have dynamic sensing in this plant, then you could have a wireless sensors, and you can, at different times, you can turn on and off those plants. For that, you will need a dynamic simulation of the plant, not the static simulation as I considered here. Okay, I will give you a dynamic simulation example later, but I just wanted to mention how this can be done. The second example I am going to talk about is water distribution network. So water distribution network, drinking water distribution network is actually simulated. This problem became very important when people were worried after 9/11 that the enemy could put any contaminant at any node in the distribution water network, and that actually will propagate the problem and affect the population. So how do you minimize the risk to the population when you have a contaminant entering in the network? This is a simple network I have taken. There are something like 10 nodes, 11 nodes, 11, 12. So the nodes, and essentially, how do you place sensors with a minimum cost in this thing? The problem also has uncertainty because demand can be uncertain. And one of the different thing here in the network of water networks, if demand changes. So for example, here, we know that population at different nodes can change. The demand, that means demand can change. Uncertainty about attacks can be different, but uncertainty, population can change, uncertainty in demand can change. So how do you find the robust solution? When we say demand uncertainty of how it affects, it also changes the structure of the network, which is different because it's not only changes the flows in the network. So for example, here I'm considering deterministic network, the same network I showed in the demand. Okay, now I'm saying that there is a 25% uncertainty in a demand, uniformly distributed. What we found is that there are structures which occur because of the demand changes, is that if you look at the node between the flow between 18 and 32, it is going in one direction when there is a deterministic demand. It goes in a different direction when the demand changes. So you have to be aware of this when you consider all the calculation, that not only if you change your decisions about sensors, it's not only going to affect the flows and things, it can affect the structure of your network. Okay. The other thing, what happens is the impacts not only affect the node itself, but downstream. And if so, here I'm just showing how no sensor population uncertainty is propagated. One is, no sensor uncertainty is propagated. So population distribution at node 11 with and without sensors. So sensor uncertainty is into consideration. If with, remember I said that without sensor, you have large uncertainty, that is the blue line. But as the network, you put sensor, your uncertainty changes. The sensor node is the green node, which has larger uncertainty, but downstream the node also there is uncertainty propagation. Okay, so you not only have to consider uncertainty at that node, but the uncertainty propagation occurring in the downstream node. Okay, So we consider four kinds of optimization: cost optimization. This is using TIVA spot with impact minimization, and optimization without uncertainty with impact minimization, and optimization with uncertainty with impact minimization. So one is cost minimization, the other one is impact minimization, and there are A, B, C, D. TIVA spot is the system which is designed, algorithm designed by Sandia National Lab for sensor placement. So we are comparing the two, and this is what we got. Okay, if you look at how the sensors are pressed differently, for method A, wherever there is A written, that's where the sensors are placed. For method B, so you can see that the node where the sensors are placed changes completely depending on what kind of, whether you're considering uncertainty or not. C and D, you look at comparing C and D. The D node for sensor is 13, 23, 31, and 32, while for C it is 12, 23, 31, and 32. Okay. So, and with and without uncertainty, you can consider with, and if cost is one thing, impact estimation is the other one. So depending on your objective, your sensor positions will change. I'm just checking the time, because I was told there is a hard time gap. Okay. So with this, I'm going to shift this thing to another example is related to dynamic sensing. As I said that dynamic sensing is important because most of our sensor networks are going to be dynamic now and that needs real-time optimization. If you look at dynamic sensing placement problem, in the literature, there are object tracking problem and adaptive sensor problem. Many of them use Bayesian updating, but it needs large amount of data and it cannot be used in real time. So with bonus, we can use it real time. So I'm going to show a simple example. This is an example of cows actually eating grass. This model is coming from evolutionary biology, where they're trying to understand the behavior of cows, whether they are greedy cows or cooperative cows. Now, how it works is that every turn, each cow looks at the patch where there is a green patch and that it is currently on, and eats a unit of grass. Okay. The greedy cows eat the grass regardless of the length of the grass on the patch, while cooperative cows won't eat the grass below a certain height. And this will continue, and the grass will grow if it is at a certain height, and the cows will change their position. So I took this example as a sensor placement example, and I'm just going to show you the simulation of cows. So there are green patches, and as the cows age, the patches are disappearing and the cow are changing position. Now my aim is to find how many number of cows I can measure by sensors. And I'm just going to put, since this are two sensors, okay? Two sensors, my aim is to find in the radius of sensors, how many in the circle around the sensor, how many cows it can measure. So my problem is, is dynamic sensor placement. And here I'm again converting into, instead of positions of cow, I'm just taking the X and Y coordinates of the sensor changing. So it becomes a nonlinear programming problem. Okay. So I'm deciding, and here I'm saying that all these cows, I'm only going to put two sensors and I want to find maximum number of cows. Okay. So here I'm just showing how we did real-time optimization, and this is a real-time optimization with bonus. So you will see the two dots are sensors. They are changing wherever cows are going. Wherever maximum number of cows, they will find those cows. Okay. So this is what we use now in the dynamic sensing. And for these cows, if you look at the objective function was how many cows, and you can see that with the fixed number of sensors, only initially you can measure the amount of cows. While with dynamic sensing, you can measure most of the time. And how the sensor positions change as time goes by is shown here at with different colors and different this thing. And you will see that the sensor position changes with cow. Okay. So with this example, we'll go to the real world dynamic sensing example, optimizing real-time spatiotemporal sensor placement for monitoring air pollutants for human health risk for city of Atlanta. Okay, this data we have collected a real world data for Atlanta. One of the things what happens is that air quality is essential for assessing health impact of air pollution. The problem is enhanced with urban areas due to pollutions from automobiles. So there are different sources of pollutions. There are power plants and things. That is a static one, but the dynamic thing is that the automobile pollution is dynamic because it's changing positions also. Okay. And so we concentrate on how the traffic patterns are, and traffic pattern demand, the traffic patterns changes as the day goes by. Okay, at some point. So so what we are saying is that there are 10 sources of sources of pollutions. This can be automobile or existing, and those points are marked here. And if you take static monitor, you may not be able to enable actual impact of pollution, because as the traffic pattern changes, pollution pattern changes. And I can show you the example. And so we could do real-time optimization of sensor placement for this study. Okay. So the aim was that timely detection of contamination for control measure. Where we had uncertainty, remember automobile change, number of automobiles at particular location, as well as the location of the things changes. The other thing is that uncertainty in meteorology also changes, wind speed, temperature, etc. That has also this thing. So we want to find the location of the sensors which are robust in under this uncertainty. Again, an optimization under uncertainty. Sorry, I was looking at watch so that I know how this. So, how much time do I have?
You have about another 5 minutes or so.
Okay, so that's good. I can finish in 5 minutes. I was just worried. So this is the problem formulation. We wanted to maximize Fisher information. That's the thing. And we use AirMod, which is an air modeling system people use in cities all over the United States and abroad. And we also consider weather and model uncertainties in the AirMod. And we considered the traffic patterns, and that's uncertainty of traffic pattern. And again, our decision variables for location of sensors all around the city, X and Y direction. If we grid Atlanta region, we can get X and Y in that. So here was the thing. As I said, 10 different sources of pollutants were identified. And we were monitoring pollutant for 10 hours, starting from morning 8 o'clock to evening 5 a.m. Okay. There is a wind speed and temperature uncertainty depending on the weather conditions we can get from the weather data. Traffic patterns, maybe from last week, you can consider that, and their uncertainty, we can capture that. And then we actually can maximize. So we maximize Fisher information obtained from pollutant distribution, and then in terms of health impact. And I may not show the health impact because the sensor positions changes depending on your objective function, but this is the thing. So health impact assessment, I won't get into this thing, but essentially it is a function of concentration of each pollutant. And depending on that, we calculate the health impact. And this is the sensor placement in a day. Okay. So this is at different time. Okay. So first 8 hours, 10 hours, 12. I'm just showing you 5 graphs. You can go hourly, you can go in a different distinct. So what we are saying is that I'm going to place 2 sensors in the city, and where there is a maximum pollution, and the pollution data pollution is shown here in blue and red and this thing. So high pollution is red case. So you will see that, and the dark blue is higher than faint blue pollution. So you'll see in 8 hours, the sensor position changes in 10 hours. Depending on where there is a high pollution, the sensors actually go near that, okay, and try to capture as much information as possible. So it does changes the position of sensors and you can use it. So that's the thing. So in summary, static and dynamic sensor is an optimization under uncertainty problem. Especially dynamic sensor placement is an important problem of today for today's age, and it needs real-time optimization. We use bonus, and I showed you some real-world applications for energy and environment. There are people who worked on these problems, and if you want to know more about your this thing, you can actually have about the algorithm itself. You can actually have a book is available through Springer. Ebook is available, and you can get it through your library. For papers, you can either contact me or go on my website, recent website. I know that there are a lot of websites come in, and you will find many of these papers are they're uploaded there. But if you cannot get it, just contact me. I appreciate your time, and if you have any questions, I would be happy to answer.
Oh, fantastic. Thank you, Urmila. That was a very great overview of some of the nice contributions you've made, especially around optimization, uncertainty, just how you've changed the algorithms to be able to handle these large scale and complex systems. So excellent work. Thank you for that. We have a little bit of time for questions now, and I'd invite you to either unmute your microphone to ask a question, or you can place it in the chat window, and then I'll moderate the questions that way. So either way is okay. So I just have one question here. It looked like there was a trade-off between cost and Fisher information for a lot of these. If you can go back to that slide, that would be great.
Yes.
Fantastic.
Yes.
And there's, I suppose, the embedded in the cost is just the cost of maintaining these sensors. And
that exactly. And the cost, no, this was only be included buying the sensors actually.
Oh, buying the sensors. Okay.
Yeah.
So the one thing I saw, working in industry is that analyzers are very expensive in chemical plants and refineries, for example. And there was always this debate, do we need this sensor here? Does that help us, operate the plant more effectively? What thoughts do you have about, instead of Fisher information, how can we translate that into benefit? I'm just wondering what kind of suggestion.
That's a very good question. So one of the ways we can do this translation of Fisher information just gives you information, but one of the things you get in these cases is the probability distribution of the outputs, so we actually can look at, so for example, you can say that if does it benefit me if my quality of my product, okay, is changing significantly because I'm not using proper sensors. So I can look at the probability distribution of quality of my product, and I can say variance is high because I'm not using proper sensors. Then you can actually, this is one of this thing.
I like that. Yeah. And that makes a lot of sense, because you give away a lot of quality, especially in refineries and blending and things like that. You add more than you need to meet a specification. Okay, great. Any additional questions from the audience? I've got a few more, but I don't want to take all the time if there are others who have some questions.
Feel free to contact me anytime if you have questions later also, okay?
Okay, it looks like we have a question from the chemical engineering, BYU chemical engineering grad student, so go ahead.
So kind of similar to Dr. Hedengren's question,
Yeah.
how much more expensive are these dynamic sensors compared to a stationary sensor? Like how many and how many stationary sensors could you replace with one dynamic sensor to get
That's
the
a
same
very,
amount of
very,
information?
yeah, very good question. Actually, we haven't done the study about comparing this. That will be a really good study to do, that can we actually replace the cost of having 10 sensors with 2 sensors, you know. We haven't done that. This dynamic sensing is coming in picture. As I said, it's a very recent concept, you know. In chemical plants, wireless sensors are becoming more this thing. So that becomes one of the things. But in air pollution, now they are thinking about having drones. You know, it's not yet done. You know, so I'm just saying it is still coming in picture. In water and all, they have portable sensing also. You know, but these sensors are not yet at the point where people are thinking about sensor placement problem. Because I was looking at nitrogen, phosphorus sensing in water, you know, for all this pollutant in actually river flows and things like that. There are portable sensors available, but right now they are just in the test phases and things like that. So, but it will be a really good thing, Ms. Ajay. This is a very good question, because we can actually compare what is, right now I'm just comparing static sensor results versus this thing. But if we compare the cost of those things, that will be really good and show benefits of dynamic sensing. Thank you.
Thank you.
Any other question?
Professor Urmila, I'm Jairam Valuru.
Hi, thank you for joining from India.
Yeah, nice. Yeah, nice meeting you. I have one question related to, so when you solve this problem in a dynamic way, so how do you account for the data quality? Because the data quality plays a major role when you solve the problem in a dynamic sense, right? So how the data quality, like effect of outliers, how it is accounted in the algorithm?
Right now, because in some ways we are actually using the models. So in some ways you can put that in terms of another uncertainty. Okay. But in these problems, we didn't consider data quality. You know?
Oh, okay. So all the data is assumed to be a normal data.
Yeah. So we just assume, but in general, they can be considered in terms of what is the error characteristics of data. You know, you can do that.
Yeah. Thank you very much.
Good question.
Thank you. Yeah.
So.
Okay, fantastic. I've got one more question.
Yeah.
And I'd like to share my screen if I could.
Yeah, I can stop.
Just kind of illustrate this question a little bit. There's okay, so can you see the map here?
Yeah.
Okay, so here's like air quality. We pay attention to this like during wildfire season, to see when air quality is bad. And then you have others like from satellites, for example, that give things like PM 2.5 over a broader range. But with each of these, these are not even gold standard here. This is, purple air. It's kind of community driven sensors in location. So if I zoom in, I can see everyone who has one of these installed at their home. So these are a little bit more accurate, but the government has maybe like 5 of them in this area. And then there's this one that's more satellite driven. So you have kind of varying levels of fidelity, but also resolution. And I was just wondering, sensor fusion is such a big deal. What can you say about your framework for dealing with not just high quality sensors or low quality sensors, but how do you maximize the information and with these different levels or layers of information that you get?
Yeah, that's a very good question. And I think I'm going to try to answer it. It may not be correct answer, but it's a very good question. One of the things is that as I said earlier, when we were considering quality of measurement, we actually assign error distributions to those measurements. So for example, some of them, when we were considering, and this is just taking example from, for example, the first problem of power systems, we said that high cost sensors will have better error characteristics. It's lower the variance is lower, as compared to low cost sensors. Or for example, sensors which are very farther away may have a higher error characteristics as compared to this. And then you may have to do data reconciliation, So it's not a easy problem, but I'm just saying there are steps which we can do to get that information.
Okay, I love this topic because of Internet of Things and other, other areas that are just exploding right now. There's this idea of, how do we use these sensors, especially low cost sensors, but maybe correct them with higher, occasional higher fidelity sensors. So excellent. Well, fantastic. Well, Urmila, thank you so much for that presentation. Very engaging. I love that you not only had some of the theory, but also a number of case studies that showed, that your research is having a big impact in several areas. So thank you for that. And congratulations also on the award. It's well-deserved. So thank you.
Thank you. I think my students and all are, one of them is here also on the talk. So I want to acknowledge them also. Kirti is there. Thanks.
Fantastic.
Thanks.
Okay. Well, thanks everybody for joining.
Thank you. Thank you. Feel free